Okay, folks. So it's going to be hard for me to check the chat. So just feel free to speak up. My lips are moving, so let me know if you can't hear me. I know that Eric could, although he doesn't seem to be with us right now. Maybe he got kicked off or something. Anyway, any questions before we get started today? Okay, so here we go then. We're going to kind of pick up where we left off. We're sort of leading into Galois theory a little bit, but I want to bring up this first theorem. By the way, I left you with a theorem last time, and I'm just going to let you kind of go through the proof and the notes. Theorem. When holler at me if you have a hard time saying. From 8.1.11. So let's let K be a field and F a polynomial of degree n. That's Kx polynomial. Then we can find a simple extension f equals k of u such as the following. The first thing is there is a root. There exists u and f. F of u. So the first thing just means whatever this polynomial is, there we can find a simple extension where it has a root. The degree of equality f of x is. I want to take a guess at this. So the degree of ku over k is. We have equality if and only if. I want to take a stab at it. By the way, I may have already mentioned this, but speak up because it's going to be difficult for me to check the chat. Anyway, how about this for a condition? F is irreducible. And if F is irreducible, you all know what an isomorphism is. Well, what do I mean by a K-isomorphism? I mean an isomorphism that actually fixes the elements of K. Such that in this case, F adjoining a root of F to K. With the smallest field that contains K, and whatever the root of that irreducible polynomial is. Okay, so if there are any questions so far, let's kind of go through the
Is
proof.
there any way you could, is there any way you could zoom in a little bit, or is it zoomed in? It's just
Yeah,
hard
I'll
to see
look at
the
this before we start. Can any of you tell me? I tried to look at the zooming the camera. I mean, I could, well, you know what? I could just try to do one board and try to get closer here. Try this. Is that better? Is that more visible?
Yeah, there was just like a weird glare from the light, so I couldn't see like part of the theorem. But yeah, that's a little bit better.
Yeah. Sorry about that. Is the other board have less of a glare? The other board is like a little bit, I don't know. Is that seeable? I can try to write bigger too. Maybe that'll help. I'll just have to erase more.
Yeah, that might help. Yeah.
Can y'all see okay if I write a little, well, let's go through the proof of this. I'll write a little bit bigger and see if that that works out for us. Proof. So first of all, let's deal with this. Suppose that we suppose that F so this F of X here factors as F of X X P2 X P in well I'll say yeah, let's say PK with each PI X. Okay, so suppose that we can factor this down here like this. And by the way, I'm assuming that each PI is irreducible. Each PI is irreducible. Each is irreducible degree at least one, right? So let me ask you this. If I look at Kx, generally about P for any one of these factors here, can somebody tell me what we know? Can you tell me what we know about the structure of that ring right there, Kx mod Pi? So what do you know about Kx itself? Well, Kx is a principal ideal domain. It's PID. Of course, each PIX is irreducible. And in a PID, that means it's prime. And again, because it's a PID, any non-zero prime is maximal. So each is a field. Okay. So in other words, if I mod out by any of the factors of F, I get a field, right? So let's consider the following one-to-one homomorphism. Is again, math, you should always try the easiest thing at least first. The easiest homomorphism I can think from K of X into here is the map that takes an element of K into its corresponding coset. And so this is a one-to-one homomorphism from K into K mod P I X. So K subfield of K mod equals PIX. We claimed in the first part there that there is a U and F such that F of U equals 0. So let's consider, let's take a specific one of those. So I'll without loss of generality, I'll just take P1X. So let's consider this field here. Or well, I'll just do PIX. Let's find the roots claimed here. Consider the homomorphism that goes from Kx, the field Kx mod Pix, given by Gx. It's the coset Gx plus Pix, right? And let me point out that what happens when you plug in, you know, a generic Gx? What happens when you plug in? Of course, this thing's already in. And so what does that get us? So this means that my root that I claim. Now, what happens what happens to X under this? This is an element of, if you look at pi X, right? This is an element of that coset such that PIU is 0. X is equal to 0. Any questions on that so far?
Hey, I have some problem hearing you when you are talking on the board.
Okay, I'll speak up.
In front of the computer, I can hear, but
So what we have now is we have that PIU is 0. That computation just follows what we did before. And notice that since PIX divides f of x, remember PIX was one of the factors of f of x. It was a product of all P1 up to PK. Then U is a root of f of x as well. And so we've established this first business that given my polynomial f of x, I can find some extension where it has a root. Okay, so for part B was that claim that that the degree of Ku over K is no more than n, and you get equality if and only if f was irreducible. So notice that part B, degree of Ku, the degree of Ku over K is equal to PIX. This follows from the theorem that we did last time on Friday. Right? So now that we've got this, it's pretty easy to see. Of course, PIX was one of the factors of F. And we'll call the degree of Fn, right? I can't remember if I called it that in the, but this will be just defined to be the degree of Fi, or the degree of f of x is n. So the degree of this is, since this is a factor of f of x, is certainly less than or equal to this. And well, remember, equality holds if and only if f of x is irreducible. And let me take you through that. I just wrote the statement down, of course, but if f of x is irreducible, that means that when I factored f of x into all the p's, there must be only one of them, namely f of x and p of x are the same up to a scalar multiple, a non-zero, and that means that that the degree of this is n, because it has to agree with the degree of f of x. On the other hand, if you have equality here, that means that when I factored f of x down into irreducible pieces, there was only one of them, so f of x is irreducible. Everybody okay with that? Everybody okay? Okay. And I'm going to leave part C. Not very difficult. If there are any questions, we'll move on to the next one. This one is actually a really cool, the next year is actually kind of a really cool one because, you know, in a certain sense, it seems like it's sort of easy to make transcendental extensions, right? It's easy to make an extension over another field where there's some things that aren't algebraic. And the easiest way to do this is to take a field and then consider rational functions. So your variable x that makes the rational function will be transcendental. But here is, this is a big sort of sweeping situation where you actually have algebraic extensions. So, theorem. Suppose you got any extension of fields you want. is finite, then F is finitely generated this is a wonderful theorem because what it says is if you have a finite extension of field, so F over K, so if the degree of that extension is finite, 2, 3, 100,000, then that extension is finitely generated over, then F is finitely generated over K. That's probably a little bit less surprising, but maybe what might not be completely obvious is that if that extension is finite, then every single element is algebraic. They all have to satisfy some, every element in F has to satisfy some polynomial over K. Okay, so by the way, any ideas why this would be true? So what do we have to do to show finitely generated over K? Every single element in F is the root of some polynomial with coefficients in K, correct? So so let you be your favorite element of the big field. Suppose that the extension field is a finite number. Well, remember what this means. This means that we have over K, the vector space. So again, one U squared U n minus one. Of course, this is a subset of forms because we've got one more the size of the basis. Right? So any set in a vector space, namely F over K, any element has to be linearly dependent. So in particular, there exists, let's say K0, K1 up to Kn, not all 0, such that K0 plus K1U plus K2U squared plus Kn UN. Well, let me do this. Let me write it this way. So there is some linear dependence relationship with these KIs not all 0, such that this polynomial or this, these linear combination of the powers of U over K is equal to 0. And suppose I is maximal such that K of I is not 0. Right? So there's some maximal such that K of I is not 0. So note that Q is root of K0 plus K1U plus KIUI. So in particular, F is algebraic over K because an arbitrary element has been shown to be the root of a polynomial with coefficients. Any questions so far? As I pointed out, I'm showing that it's fine. Okay, is even easier. So let's go through that part. Suppose one, V2, V3, a basis. Much stronger thing. Because notice every element of F is a K-linear combination, right? In a rather sloppy way, F is equal to K adjoined with these things. Once you have K and you have these VIs, then you have every K-linear combination of VIs. And actually, on the surface of it, this seems like it's connected because you've also got things like V1 squared, V1 cubed, V2 to the fifth power, things like this, which might not appear to be written as a basis, but because these elements are all algebraic, you can redo those powers and again write them as a linear combination. So it follows very quickly that as a field, F is finitely generated because all you need is those finite number basis elements. Any questions? Let me make a remark also that occurred to me as things were going on that I don't think I pointed out yet. Let me ask you. So I got a little quick short quiz for you. Suppose I have a homomorphism phi from K to R, where K is a field, R is a commutative ring with 1, and I'm going to assume, as is usually the convention when you're working with commutative rings of identity, I'm going to assume that this phi takes the identity of K to the identity. This is really open-ended, and I apologize for this, but I'll ask it anyway. Anybody tell me anything about that homomorphism phi? So it's very important that the domain is field and that it takes 1 to 1. Can anybody actually? It's not just a homomorphism. It's got an adjective. Does anybody know what it is? Let me ask you this. What are the possibilities In such a situation, what are the possibilities for the kernel of phi? Anybody? This is just full person here. If the kernel of phi has anything other than 0 in it, remember, the kernel of phi is the kernel of phi is an ideal of the field. So your choices are really 0 ideal for all of K. Those are your choices. Well, it can't be all of K, because if it was all of K, that means that takes everything to 0, including the identity, right? So we rule that out. And so the kernel is 0, hence phi is 1 to 1. So if you ever have a bona fide homomorphism from a field into a community of ring with identity, in particular, if you ever have a homomorphism from one field to the other field to another field, it is always injected. It's always 1 to 1. And I think that's an important observation for later. Okay. The next theorem is also another extremely important theorem, and it has to do with the transitivity of the notion of algebraic in the following sense. A, B, F, if is algebraic over M, and F is algebraic over E, over E. Algebraic over. So this is I like to refer to this as sort of transitivity of the notion of algebraic. However, let me give a fake proof first, because I think this sort of lends to intuition. This is very easy to prove. Bootstrap off of what we just know. Let me point out that if let me point out that if E over K is M, and F over E is N, so these are fine, then P of F over K is the degree of the degree of E over K. Remember, our proof is that all finite extensions are if so also algebraic. So this is something that follows point out that extensions do not have to be finite. And in fact, can anybody give an example? Algebraic extensions do not have to be finite. It's just finite extensions have to be algebraic. Can anybody give an example of an extension of Q? Let's say rational numbers, make it easy. That's not finite. Or can you give me a construction that will give something? So here's a good example to kind of think about. And I think it helps. I think it might help you think about big things. This is Q, and this is the smallest field that contains Q in the square root of 2, right? This is, we've done this construction already in class. This is QX modulo the irreducible polynomial x squared minus 2, because that's the polynomial that's 2. Now take the square root of 2. Now this extension is degree 4 and it's algebraic. And you might at this point see where I'm going with this. Now let's let F equal the union take the union of these fields. Notice that in a certain sense you can consider Q is contained in this, which is contained in this, which is contained in this, and so forth and so on. Let me make a quick argument that F is in fact a field, right? This is the union of these nested fields, bigger and bigger. So take any two elements of F. One of them's in Q adjoined with 2 to the 1 over 2 to the n. One's in Q adjoined with 2 to the 1 over 2 to the m. Just take whichever is the bigger of the field, add those two elements up. It's in the bigger field and hence in the union. You can do the same thing with products. This is in fact the field. This field is algebraic because if you pick a random element out of this field, it's in one of these in this nested chain. But if it's in one of these fields in the nested chain, it's algebraic because every one of the fields in the nested chain is a finite extension Q. This is of degree 2, this is degree 4 over Q, degree 8, and so forth. Everybody okay so far? So this is an algebraic extension. Every element is in one of these things, so it's algebraic, but it's not finite dimensional because of the fact that this is a nested chain, right? In fact, there are elements in this field that have minimal polynomials of arbitrarily high degree. Okay. Everybody okay with that? So this shows that you can't just do this triviality here. So let's actually go through the proof that algebraic is transitive, right? So what we want to do is we want to take some element in F, right, and show that it's algebraic over the base field K. So proof. My goal is to show that U is algebraic over K, but all I've got at this point, excuse me, all I've got at this point is it's algebraic over E. Now, U is algebraic over the intermediate E. So there exists E0, E1 up to En, all in E, such that U is a root of E0 plus E1x plus E2x squared plus ENXN polynomial over E. So we've got that much, but the problem is, of course, the problem is now we've got U being a root of that polynomial there on the bottom with coefficients in E. That's just not good enough. We need those coefficients actually to be in K. So let me point out something here. This is kind of we have this equation here. En E I will assume that En is not because if it was 0, I would write this down. I would just start. I want to point out that this equation shows that U is algebraic over E. But that is actually overkill. I didn't need everything I need to make U algebraic, right? All I needed to make U algebraic are these n+1 coefficients. So I don't need all of E for this to be algebraic. I just need E0, E1, all the way up to N. So this observation U is with the N. Like, all you really need are those coefficients. Everybody okay with that? Now, look at the following tower of fields. You're right over here. Let me go up every time here. And finally, check it out. This is finite. Why? Because E0 is algebraic over K. So we already have a theorem that if E0, so what I've done is I've taken K, I've adjoined E0. E0 is the root of some polynomial, say a irreducible polynomial of degree K, okay, let's say T, then this is a finite jump of T, so it's finite. This is finite because E1 is algebraic over K, which is contained in K E0. So if E1 is algebraic over K, it's certainly algebraic over the slightly bigger field. In fact, the minimal polynomial that you need over K might be reduced to a smaller polynomial over here. But in particular, this is also finite. And the process continues. Each one of these jumps, when you add another e, is a finite jump because they're all algebraic. And finally, when you get here, u is algebraic over k e0 n. So this is also finite. So the whole kit and caboodle this tower is a finite number of steps, each of which is a finite jump. And so the whole jump is finite. So K, E0, E1, En, U is algebraic over K because it is a finite extension. And that means that every single element in this field is algebraic over K. In particular, U is algebraic. And we're done with the theorem because we've shown that an arbitrary element of F is actually algebraic over K. Any questions on that? I cannot resist pointing out that what it means for U to be algebraic over K is it is the root of some polynomial. What polynomial? This proof does not ever explicitly give you the polynomial. It just shows that there must exist one. These kinds of proofs show up in some kinds of commutative algebra and in field theory like this. I know it's algebraic. I know that out there somewhere there's a polynomial, but this construction here, where finiteness always gives algebraic, gives us the existence without ever producing it, which always means that there's something that's kind of deep going on in my book. Okay. Let me give you an incredibly powerful and really and I'll give you the kind of proof because it goes quite well. So corollary. So let's suppose that we have two elements that are algebraic over K. And alpha beta elements of a larger field. Algebraic over. So these are two fields, K field and alpha and beta are just two elements that I can find, perhaps in some larger field that's algebraic. Then plus minus beta, alpha beta, and alpha over beta, if beta is not zero, over K. And this, my friends, is not obvious. And we get this from this previous result. So K is in F, then alpha is alpha over K is a subfield. F In other words, algebraic elements are closed under addition, subtraction, multiplication, and division, as long as you're not dividing by zero. So the algebraic elements inside an extension FK are always form a subfield. Think about that. Also, I am going to do an example next time where we sort of explore the beginnings of the fundamental of Galois theory. I'm going to give you a chart and talk you through it. And basically in that will be the seeds of all Galois theory. So you might think of the smallest field that contains all the roots of x cubed minus 2. Think about all the fields that might be between Q and the smallest field that contains all those roots. And we'll talk about that next time. Any questions? Y'all got any questions? Yeah, I know that this is not optimal. I hope you all could. By the way, this looks backwards to me. Are you all seeing my board written correctly, or does it look like I'm writing like Da Vinci?
No, it flips it, so it looks
Oh.
right.
Good. Okay, I thought I was having a stroke for a minute. So, all right, that's all good. Listen, y'all have a good one, and we will see you Wednesday. Give me a holler if any questions come up, and I'll get back to you as soon as I can. See y'all.